Hello once again for Malus Without Superposition, Part 2. This time it's for electrons. Well, you recall that in the Part 1 we said that photons, which are electromagnetic waves, are trying to go through a filter, polarizing filter, would not go through if the angle of polarization is opposed to the angle of the filter. But it would if it is connected with, if it's parallel to the filter. And we were trying to explain what happens at an intermediate angle, and at 45 degrees, half of the time the photon goes through, the other half it doesn't. But at other degrees, it takes more explanation. And it turns out that the rate of passage is dependent on this angle, cosine of this angle. And the rate of failing is also related to the cosine of the angle, and the ratio of the passing to failing is cosine squared over sine squared. Well, why is that? Now, your conventional explanation is that there's superposition. The frisbee is like two frisbees. Well, it's not that the frisbees there's two frisbees that are, one is partly this way, partly that way. It's that the probability of the passing of the frisbee is superposed between two vectors, one of length sine theta in this direction, one of cosine theta in the other direction. Well, it's not that the probabilities are superposed, it's the probability amplitudes are superposed, and you got to square those amplitudes to get the probabilities, which is the law of Malus. Now, instead of having superposition, what I'm thinking is that when the photon frisbee enters the filter, it encounters this cloud, a Brownian motion, that it wants to push the photon either passing or failing. So, the photons, the Brownian motion vectors that will succeed in pushing the photon into the pass direction, are aligned like this. It have length sine theta. Well, and then to make it fail, you have to have a vector in this direction of that length. Well, there's exactly one vector like this, but I'm thinking what we said before is that there's many vectors that have this component, and there's like a cone of these vectors inside this Brownian motion. So, ball. And this ball of vectors looks like a shrub, a bush like this. If you're an atom, that's what it would look like. Then, so then this cone is the ratio of this cone to that cone is the Malus ratio. And what's the size of this cone? Well, the size of that disk on the bottom of the cone is this radius squared times pi, and that's cosine squared pi. And then the radius of this cone is sine pi, so its area is sine squared theta pi. So we get this cosine squared over sine squared ratio, which is exactly the law of Malus. So that's very successful explanation. Now, there's more than just photons. There's electrons. So electrons are not everybody. Electrons are point particles, but they have spin, and the spin could be up or down. In fact, whenever you send an electron through a filter that checks for up or down, all you get is up or down. You don't get any partial intermediate angles. Even if you prepare your electron at an intermediate angle. But if you prepare it at 45 degrees to the filter, half the time it'll register up and the other half the time, or I guess this is what I mean is this, 90 degrees to the filter, it will say it's up half the time and down half the time, which agrees with your intuition. But at intermediate angles, what happens? Well, once again, we get the law of malus, depending on this this angle theta. But it's, once again, it'll be cosine squared and sine squared, but it's not going to be of this angle theta. It's going to be half of that. If you call this angle actually of incidence, 2 theta is really going to depend, these passing and failing is going to depend on this angle theta, which is, half that angle. And if you remember your high school geometry, if these are equal, and that's collinear, then this is double that angle. And you also have to remember that this, when you draw this triangle from here to here to here, you get a right triangle. So now and once again we encounter this Brownian motion ball, but it's limited. The power limit is not 1, it's 2 this time. So the how many vectors will be successful in pushing this spin vector either to the up direction or into the down direction? Well, once again we get the cones. But this diagram is a little bit different. So we have sine theta in this direction and cosine theta in that direction. And the size of the cones are, once again, the ratio of the cone size is cosine squared over sine squared. And you get malus again, without superposition. And also you don't have to express the angle of spin using 2 complex numbers, which would make it a 4-dimensional vector. You just need the 3 x, y, and z. And then when you add this vector, when you take this vector and the angle and this other vector, which is the axis of the filter, you get this 2-dimensional coordinate system like that, which is a very simple simplification. And it gets rid of the magic and replaces it with geometry. So, pretty happy about that.